Hello everyone, my name is Rinki Tyagi, working as an assistant professor in Information Technology Department in Akgec Engineering College. Today, this is my second lecture on Computer Organization and Architecture series. Today, we will study about bus arbitration. This topic is very important as 7 marks long question comes from this topic most of the time, and also very important for GATE. As I mentioned in my last lecture that this subject consists of 8 to 12 marks in GATE. So this topic is most important for GATE purpose also. So today we will study bus arbitration, daisy chaining method. Today we will study bus arbitration, daisy chaining method, distributed arbitration. Basically, daisy chaining method and distributed arbitration is a type of bus arbitration. In next, we will study general purpose registers. So these are the topics that we will study today. So in my last lecture, I told about bus and types of buses. So to move data from one bus system to another bus system, so to move data from one device to another device in computer, like from memory to CPU or from peripheral device to CPU, we need buses. To transfer data, we need data bus. To fetch data from memory, we need address bus. So because address bus will fetch address from memory and will give, and then data bus will fetch data from memory through that address. And last one is control bus. Control bus is used to send the signals to rest of the buses. So today we will study bus arbitration. So why we are studying this topic? First, we will I will let you know that why we are going to study bus arbitration. Basically we are sending lots of data through wires. So there are huge collection of wires, and there can be a collision of data. So to improve the functionality to transfer the data, we need a bus arbitration, so that there will be no collision in data and data will not be leaked or data will not be lost. So here we have written here that we have processor and DMA. That is we have direct memory access controller. When we want to directly access the memory, then we use DMA controller. Both need to initiate data transfer. So here processor and DMA both are going to transfer data on the bus and access main memory. Data can be fetched from memory also. So DMA and processor can also access the data from main memory. The device that is allowed to initiate transfer on the bus at any given time is called bus master. So the device which is initiating the transfer of data, as data is flowing from one device to another, so there may be a device which will initiate the data transfer. So that device is always known as bus master. When the current bus master relinquishes its status, when the current master will get its status as the bus master, another will acquire also their status that they will not be the bus master. Only one device will be the bus master. And when the bus master will say, now I am not a bus master, I have completed my task, then from the rest of the devices, one device will get the status of the bus master. The process by which the next device become the bus master. So the whole process, when the bus master relinquishes its status and the next device is getting the status of bus master, so the whole process is known as bus arbitration. So this is a very important topic. Now we are going to study what is the potential of bus master, what is the need for arbitration, and what is the potential for bus master. So basically bus master scheme, a bus master wanting to use the bus asserts the bus request. Basically bus master using the scheme of bus asserts will assert the request. The bus master cannot use the bus until its request is granted. So first the request will be granted to the bus master, then only the bus master will acquire the status of bus master. The bus master must signal to the arbiter about finishing using the bus. So bus master will signal that the arbiter will use the bus or not. Bus arbitration usually try to balance two factors. So basically there are two factors on which bus arbitration scheme will work. It will focus on two factors. First one is bus priority and second one is fairness. First is bus priority, as I told, and second one is fairness. So the device will always be given to the, or the service will always will be given to the device that has highest priority. The highest priority device should be serviced first, as it is written here. Next is fairness. What is the meaning of fairness? As I told that the device will will be given first the service that is that has highest priority, but there can be a device that will never get a highest priority, so it will never be serviced. So fairness will work on that part. Even the lowest priority device should never be completely locked. That if a device is of lowest priority, it will never be completely locked out from the bus. It will wait for their turn. It will never be locked out. Like it will always, as I told, that the highest priority will highest priority will device will get the service first in bus arbitration, but there can be some time that the device will be of lowest priority. So in that case, what will happen? In that case, a device will never be completely locked out. It will wait for their turn, and when it will get the priority, it will be getting their service of bus arbitration. So basically bus arbitration is basically divided into four types, that is daisy chaining arbitration, centralized arbitration, parallel arbitration. We will study all this part in next slide. First one is daisy chaining arbitration. As it is written here that this is bus arbitration, there are number of devices connected here, that this is a device 1, this is device 2. As I said, there can be a number of devices, like we have, if we have 4 devices, then it can be a device 4. If we have 10 devices, it will be device 10. So there can be a number of devices, and devices will be according to the highest priority. Device 1 will be of highest priority, device 2 will be of second highest priority, and device N will be of lowest priority. So bus arbiter will send the signal to the device only to all the devices. Here the signal is sent to all the devices. Here the signal is released to, it is requested that the request signal and the release signal is always given to all the devices. But only that device will be get the bus arbiter that will send the grant signal to the bus arbiter. So what are the advantages of daisy chaining method? It is a simple method, but if the signal will travel, the only it works, it can, but the only disadvantage with is that it cannot assure fairness. In last slide I told about, fairness, that even the lowest priority device should never be completely locked out from the bus. But daisy chaining method is not working on that scheme. Daisy chaining method is saying it cannot assure fairness. A low priority device may be locked out indefinitely. So basically it will only work on the first scheme of the bus arbitration, that the highest priority device will get the bus, but it will never work on the fairness part. The low priority bus device may be locked out indefinitely. This is the use of the daisy chaining method. What is distributed arbitration? The device wanting to use the bus share the responsibility of carrying out the arbitration process. Here number of devices wants to send the data or to receive the data. They are so they are in waiting state, whether they have to send the data, whether they have to receive the data. They are always in waiting state. Bus arbitration does not depend on a central arbiter. Here in central arbitration, there is a central arbiter in which, like in daisy chaining method, as I told, like in daisy chaining method, there is only a one arbiter, that is a bus arbiter. Everyone is waiting for the signal from bus arbiter. But this is the only arbiter. But in distributed arbitration, it does not depend on central arbiter. Here the bus will share the responsibility of carrying out the arbitration process. First, this is the first advantage of distributed arbitration, that it does not depend on central arbiter. So here a 4-bit ID number will assign to each device. There are n number of devices, device 1 up to device n, depends on the value of n. So each device will be assigned a unique 4-bit ID number. all the devices are connected using 5 lines. Here 5 lines, all the devices are always connected through 5 lines. Among them 4 are arbitration line and 5th one is the line that will transmit the ID, and 1 line is for start arbitration signal. So basically there are 5 lines to request the bus a device. When we want to request the bus that it need to request, so it starts the start arbitration signal. It asserts the start arbitration signal. It will assert the start arbitration signal and places the 4-bit ID number on the arbitration line. It will we have a unique 4-bit ID number. Only with the help of that unique ID number, it will analyze the device, on which device it is sending the data, or on which device it is sending the signal, or receiving, from which devices it is receiving the data, or from which device it is receiving the signal. So basically this is the most important part in distributed arbitration. The pattern that appears on the arbitration line is the logical OR of the 4-bit device ID. So here the main focus is on 4-bit device ID. So to analyze this to analyze 4-bit device ID, there will be a pattern. That pattern will work on logical OR. That pattern will work on logical OR operation, and it will be placed on arbitration line. What distributed arbitration? Let's see some more important concepts of distributed arbitration. Here device A has ID 5. Let us suppose that there is a device A that has ID 5 and it is it wants to send the request to the bus. So what is the binary of, here we are writing the binary is 1, 2, 4, 8. These are the place values in binary, and we want to write in binary 5. So this is 1 and this is 1. 4 plus 1 is 5. So in binary we will write 0, 1, 0, 1 is equals to 5. This is the binary of 5. So 0, 1, 0, 1 is the binary of 5. So there is a ID 5 on the arbitration line. Device B has ID 6 and wants to request the bus. Device C also wants to 6 also wants to request the bus. And what is the binary of 6? 4 plus 2, 6. So 1, 1, 4 and 2 will be 1, and rest of the place value will be 0, and it is equals to 6. It is written here, transmit the pattern 0110 on the arbitration line. Pattern that appear on the arbitration line is the logical OR of the pattern. So we will do here OR operation. What is the truth table of OR? If there is single 1, we will always get 1, where the second value will be 0. When both the values are 0, we will get 0. Let's see the truth table of OR gate. That is A, B and Y is the output here. They both are input and this is output. So we have value 0, 1, 0, 1, 0, 0, 1, 1. In OR operation, what will happen? 0, 0 is always equals to 0, 1, 1 is 1, 1, 0 is always 1, 0, 1 is always 0. Basically, we are doing addition in OR operation, but 1, 1 is not 1, 0, it is always equals to 1 in logical OR. Pattern 0, 1, 1 appears on the arbitration process. So when we add 5 and 6, when we will do the logical OR of 5 and 6, let me correct myself, it is not addition, it is logical OR. So 1, 0 is 1, 0, 1 is 1, 1, 1 is 1 and 0, 0 is equals to 0. So pattern 0, 1, 1 appears on the arbitration line. Pattern 0, 1, 1. This is the pattern 0, 1, 1 appears on the arbitration line. What is arbitration process? Here each device compares the pattern that appears on the arbitration line on its own ID starting with MSB. Here there are 4 bits. This is the LSB and this is the MSB. LSB is least significant bit and MSB is most significant bit. So the rightmost value is LSB and the leftmost value is always MSB. Here it will compare the MSB bits. So it will compare this value. It will compare the MSB bit. If it detects a difference, it transmits 0 on the arbitration line. If there is a difference, it will always send 0 and For that and all the lower positions, device A compare its ID 5 with the pattern 0101. Device A wants, here it is written device A has ID 5. So it will compare with the pattern 0101 to the pattern, to the resultant pattern, that is 0111. It detects a difference. It detects a difference at position 0. Here it is 0, MSB is also 0, here it is also a 0. 0 here represent difference. It transmit a pattern 0100. So it will transmit 0100. It will do the logical OR of both the operations like 0101 and 0111. When there is a difference, 01, it will not do this. It will so the pattern appear after doing the difference, that is subtraction, we will get 0110. This pattern is same of device B. Device B is 0110. So here device B has won the arbitration. In daisy chaining method, there is no comparison between which will firstly get the device. It is only based on the priority of the bus. But in distributed arbitration, as we will see, first we will compare both the IDs, then we will get the binary of ID 5 and ID 6, and we will do the logical OR, and we get 0111 here. Then we will compare both the MSBs of ID 5 and ID 6. When we are detecting 0, we will do the difference. After difference, we are getting 0100. After difference of 0100 and 0110, we are getting 0110. How we will do that? Subtraction? Here, A minus B is always equals to A plus 2's complement of B. 2's complement of B. What is 2's complement of B? First, minus B is equals to B complement plus 1. What is the value of B here? The value of B is 0110. 0110. Iska minus B. So 1's complement of B is 1001 plus 1. So 110 carry 1 01. So here we are getting the answer 0110. So here this device will win. Next topic is the types of register. There are number of registers in CPU that we are going to use. What are the need of registers? Sometimes we want to do the processing fast, and we need to, so in that case, some data is intermediate data. Like in my last lecture also, as I told that if A is equals to 5 plus 2 plus 3, so 5 plus 2 have some value, and then plus 3 have some value. Then 7 plus 3 is 10. This 10 will be stored in memory. But what about 7 and 3? What about the intermediate value? These intermediate values are always stored in register. So there are number of registers in CPU for fast processing. When there are some data from peripheral devices sent to the CPU, directly to the CPU, and that data will be stored in register, not in memory, for fast processing of data. So there are number of register. First one is accumulator register. It will store the initial data. Whatever will be the initial data, it will always be stored in accumulator register. Also intermediate data and results can also be stored in accumulator. The next question is, what type of result will be stored in accumulator? The type of results that will be stored in accumulator is made by ALU. And after that, the result will be transferred to memory buffer register. In our next slide, in our same slide, we will see memory buffer register after some time. Next is program counter, that is PC register. What is program counter? There are number of instructions in a program that are going to be executed. So what will be the next instruction that is going to be executed is that instruction address is always stored in program counter. So what is program counter? Program counter always stores the address of the next instruction which is to be executed. What is the purpose of program counter? The purpose of program counter is to do the fast execution of a program or on any instruction set, because if we have the address of the next instruction which is to be executed, it will be directly sent to the CPU, and then CPU will directly fetch the instruction. It will not take time to fetch next instruction. So that is the purpose of using program counter. It is a very important register. Keep track of the memory location of the next instruction to be fetched. So it will always keep track of the next instruction which is to be automatically fetched. The program counter then passes the next address to the memory address register. After that, it will pass this address to the memory address register, and this is also known as instruction pointer register. So another name of program counter is instruction pointer register. Whenever anyone will ask what is instruction pointer register, don't get confused. Always write the answer of program counter. Next is memory address register. Memory address register, as known by their name, memory address register. So it will always store the address. It store the memory location of instruction. It will always, as I told, it will always store the address of the location that need to be fetched from memory. So whatever instruction, whatever data we need to fetch from memory, it will store. Like we want to fetch the data of A, yeah, we want to fetch the value A. So A have some address in memory, like it have address 22302. So memory address register will store 22302. This is the work of memory address register. Next is memory buffer register. Memory buffer register is also known as memory data register. Memory buffer register is also known as memory data register. So it will always store the data. It stores instruction fetched from memory. It will always store the instruction which is fetched from memory, or any data that is to be transferred to and stored in memory. So here memory data register will store 10. That is the value of A. Memory address register will store the value of this location, but the data on this location is always stored by memory data register. Next is instruction register. It stores the most recently fetched instructions. There are a number of instructions that we are going to use, but there are some instruction, those are most recently used instruction. So it will always store the instruction register will always store the most recently fetched instruction, because whenever we need these instructions, we will directly take them from instruction register. We don't need to go backward and fetch the address of that instruction, and then data will be fetched from that data. It will take some time. Those instructions, those are mostly recently used, those are stored in instruction register, so that we can get so that our program can get easily coded and executed. Next register is instruction buffer register. The instruction that is not to be executed immediately. There are number of instructions. Most recent instructions are in instruction register, and instruction buffer register, the rare instructions are used, those are not most recently used. So rare instructions are always used in instruction buffer register. Next is input output register. These are basically store the data directly from peripheral devices. We have input output devices on peripheral. So specify the address of particular input output device that is sending or receiving the data. Input buffer register used for exchanging data between, whenever we want to exchange the data from input output device to the processor, from processor to input output devices, we need to use input output buffer register. Stack control register, basically, as I told, as we all know, as we studied in data structure, stack is basically a data structure, type of memory, a data structure, method in which data is stored in memory, not a type of memory, a method which is stored through which a data can be stored in memory. So a stack structure is like this, and it is always use the concept of LIFO, that is last in first out. Last in first out. You all have, must have studied in data structures, last in first out. So like as I told, we have A is equals to 5 plus 2. So last in first out is first 5 will stored here, then 2 will store here, then plus operation will be done. So plus is on top of the stack. So 5 plus 2 7. Now it will be assigned in A. So the final result is A is equals to 7. This is the working of stack control register. Now, next is flag register. It indicates the occurrence of certain condition during an operation of control unit. And next is data register used in micro. Basically, they are used in microcomputers to store data temporarily that is being transmitted to from a peripheral device. Thank you very much. In our next slide, we will study general purpose register or common bus system or different most important topics of unit 1. Thank you very much. That's all for today.